Welcome back to COMP526 Efficient Algorithms. And a new exciting unit, Unit 6, we'll talk about text indexing. And that's in a way a problem we've looked at before, string matching, finding a pattern in a long string, but flipped on its head, where this time we spent time on the text and then try to be really fast with the pattern. It's also, apart from this, another area where we'll dig relatively deep, but we can go there by little individual steps that where each step is really easy to follow or is very fundamental. But if you put them all together and you take a step back, you say, "Oof, how did we get there? This is amazing." It's some of the smartest and coolest ideas we'll see. So I hope you enjoy this as well. But we'll go slow and we'll spend some time on it. We'll cover some things that you may have heard of. So briefly inverted indices, but then mostly suffix trees and their friends. If you haven't heard of those, then don't worry, you will. There's some generalizations of that. I don't know. I'm just listing these at the beginning, so you can at the end refer back. But some of them might not help you too much at this point. As always, I want you to know not just that these things exist, but when they are good and what limitations they may have. And we'll look at, for some of these data structures mostly, there are some nice tricks to use them for more than the initial thing we designed them for. And some cool algorithms. Let's start with setting the stage a bit for this. And what text indexing is all about. It's also sometimes called offline text search. The idea is, as in string matching, we have a text and we have a pattern. We try to find, in the easiest way, exact matches, exact occurrences of the pattern as a substring of the text. But we pre-process the text and assume that we can reuse that index that we built many times, so searching for many patterns. This term index, like index finger, is a very old one. It has the word pointer in it, which is really neat from a computer science perspective. It's, in a way, trying to build something that points you to the right position right away. And okay, I think I'll have this later again, but traditional books, at least monographs, textbooks, they often have an index at the end where they have certain key topics or key terms that are listed, and then there's the pages on which they occur. That's very close to our task, except that it's a bit more narrow, and some person has to sit down to build the index meticulously. The whole idea is much more general. All search engines basically do that. If you look up some more specific databases, pretty much everything now has a search, and people expect that to be blazingly fast. You type, and you expect within milliseconds to see some results. It goes further than that these days. You expect it to pick up mistakes you made in typing, or you expect it to find things if enough other people found the same thing by mistyping it the same way or using a synonymous word even. It goes much beyond that for search engines. We'll stay at the exact matching part for this unit. All right, another important area that during the pandemic has risen to much more fame is all the bioinformatics applications of this. You can identify certain areas in genomes, genes, areas that get translated to proteins, and many other parts. And one, just as a fun fact, if you want, 1 week after the release of the sequence of the coronavirus, SARS-CoV-2, the virus genome, 1 week after that, Moderna started basically putting their vaccine trials into production. It took them 1 week to tailor their approach that they had developed to a new virus. There's lots of computer science involved in that. Of course, a lot of other techniques and a lot of biology and wet lab techniques as well. But there's a lot of searching going on for pattern and comparing strings. A classic solution is what in computer science we would call an inverted index. It's inverted in the sense that a normal book has easy ways to jump to a certain page, say, and then you can find what's on the page. And the inverted index says, where do I find a certain word? And it tells you where the page is. So it's the opposite. The normal book, you go from page number to text, what's on page 7. And now you can ask, I'm looking for this word. On what page do I find it? So that's a simple mapping of, say, a list of keywords to the pages where they occur. That's in the classic book, or of course, computer science, we might not just have the page, but the exact index. If that's one long string, we can jump to a specific position in that string. There's some assumption that comes with this, which is totally fine for many applications. Namely, we know what strings are potentially searched for. If you think about books again, someone has to decide which words to put in the index, and the and all these very frequent words that also don't have a very specific meaning. They are not usually included. And if you would include them, they would occur so many times, it's basically useless. And so it assumes that someone decides what words to put in, and it assumes that there are words to start with. So inverted indices usually go through the text, somehow have a mechanism to split that into words. Say in the usual sense, white space separates words. For natural language text or say English text, that would work fine. And often we do an additional step that we won't talk further about it, but there's libraries that do that for English fairly well automatically. You go from a certain occurrence of a reflected word to the stem, go from plural to singular, go from conjugated verbs to the standard form. You may know your grammar better than I do, what the appropriate terms are in each case. This is just to make sure that if you look for go, you also find all these other occurrences that are logically the same word. Now, in terms of a data structure question, how would you store this? So suppose you have collected the list of words that you would like to find in your text, and you're going through the text while you do this. So whenever you find a word, you know where it was because you're just reading that position in the text. Have you seen some data structure that would potentially be useful for that? Any ideas? Yeah, for example, some binary tree. In a way, it's just a dictionary. So you can use whatever type of implementation for a dictionary you want. It's a mapping, right? It's a mapping from words to, say, a list of indices of all the occurrences. So, for example, a binary search tree would be one implementation. And of course, because you're all starting to prepare for the exam already, you know that in the expected case, at least, that means logarithmic time. Well, side note, if you want that to be worst case, you can use a balanced binary search tree. I haven't discussed how these work, but I mentioned that they exist. And so, okay, just to make that explicit, the keys are the words, and the values are lists of indices. Okay, as I don't know, list of offsets maybe. I don't want to use the word index again. So the starting position of an occurrence of that word. That's what it's meant. Cool, done. So that was a short unit, right? There's a few things where we can improve on this. First of all, we are having a very specific dictionary. Now, I've already asked this question last time, so let me maybe just pull it up again. But you will have answered it already. And we already know what the result was, namely a lot of you don't know tries. Okay, you're changing your mind now. You've looked it up. So why don't we stop with the binary search tree? Log n is not too bad, but we will be able to do better. And the reason we can do better in this case is that we have a specific type of key. We have strings as keys, the words. And so we can exploit that this type of key is special to speed up the searches. The simplest way to do that is called a try. And so let me go over this slowly. It's in principle a very harmless and simple data structure. And it's worth understanding how it works and what the trade-offs are. Even though, I mean, the plain form we're discussing now, nobody uses, and I'll show you why in a second. First of all, it's a dictionary data structure that has strings as keys. I've already commented on this slightly awkward naming convention. It's spelled like in retrieval, but pronounced like try, to not have another word that sounds like tree. It's based on character comparisons, or simple comparisons, as we had it for string matching. Now there's an assumption to make our life a little easier, namely that all the strings that we store are prefix free, which just means no string is a prefix of another string. You can either get this if all the strings happen to have the same length, then no string can be a prefix of the other. If they're all the same length, they just can't be. The other option is you make it a convention and say there's an end of string marker. And depending on how much experience you have with low-level programming, this is actually not too far from what C represents strings like. There's a specific character in the ASCII character data, in the ASCII character set, the 0, as a character. It doesn't map to any real character. It maps to the null character. And in low-level C programs, strings are represented as null-terminated strings. So you have a list of all your characters, and then there's a special character saying you that's the end. Other languages represent strings differently. They explicitly store an integer saying that's the length, that's the number of characters, and then there's a sequence of characters coming. Both exists. Now, Java uses the version with the length. What does Python do? Not 100% sure. I would suspect that a string might just be an array at the end. I'm not sure what they do. I'm not sure. I can look that up. Either way, on the theory side, both is fine. It's not a real restriction. We can always add such an end of word character. You'll see this dollar many, many times in this unit. So get used to it. That's just a way to write this end of word character. It's a character that doesn't occur in strings too often. It's common use to use the dollar for this. And it's much more convenient to have this as something you can draw, as opposed to this null character that doesn't have a visual representation. But of course, you could just replace this with something else. Here's an example of such a set of strings where we added the character at the end, so they're all prefix free. And now, what is a try? A try is a tree where we have a root, and then the child edges of each root are labeled with one character. So in this case, the alphabet for these strings is just A and B. So all the edges here are labeled with either A, B, or the dollar. We add that to the alphabet. I'll just write it as this in this weird way to emphasize there's an alphabet where the symbol doesn't occur, and then we add it to that. It must be a new character. Right, so okay, we have nodes and we have edges with labels. And what's the deal with the labels? If you follow down some path in this tree, let me mark it maybe. then you arrive at some leaf, and if you read aloud the letters A, B, B, dollar, you get the string that's stored at this leaf. The fact that we assume this prefix freeness means we always end in a leaf. If we had one string that was a prefix of some other string, then we would stop reading and still be in the middle of the try. If we add this dollar marker, we always end in a leaf, so that's a bit more convenient. Then we can always say the internal nodes are never the end of the string, and the leaves are representing the actual strings in the set. So far, so good? That's also all. That's a try, or a standard try. As you can see, there are some nodes that only have a single child, and there sometimes is a long chain of such that just goes down to one leaf. So maybe you already smell that there's room for improvement, but that's one way to do it. Now, if we wanted to find a string in this, remember it's a dictionary, we're supposed to be able to find a string. What we would do is just take the new string we're looking for, start at the root, and traverse pattern, well, character by character, following the edge that's labeled with that character. If we ever get stuck that way, it means the key is not contained in the dictionary. So one example, so we're checking, is BB in the set? I would start at the root. I guess I have to add the dollar for that to make sense. So I would start at the root and follow down this path, reading the first B. I would follow another B, reading the second B. And now I want to read a dollar sign, but there's no edge with the dollar. So at this point, I'm falling out of the tree. And so the answer must be no, because I couldn't complete my search. Had we been able to continue all the way down to a leaf, we would have found the string. And then again, as for dictionaries, for binary search trees, the leaves will have another pointer storing the value that's associated with this. In the inverted index, the list of all occurrences. But that's just baggage we carry around, so I won't usually draw it. So far, so good. That's tries. Let's see. Unlike some of these questions I had in the past, all you need to answer this question was on the previous slide. And you can see the question, etc., on the thing. So I'm going back there. So this just requires thinking and understanding of the structure. So I'm trying to test you on this. Okay, I have 25 votes, but how many people voted earlier? 50. So I'll keep it open, but I want to show the results already a bit. So it shows you that there's some favorite questions, some favorite answers, but a lot of questions have Got some votes. Now it's lots of answers. If I keep this open for too long, will you all gravitate towards whatever's the current majority? I'm not saying that that's the right answer, guys. In fact, right answer is there. So the yeah, you know, it's not useful to change your answer now. The right answer is linear in the length of the pattern that we're looking for. And let's briefly examine that again on the example that we've just done. We can just reuse the blue part. So Q in this case would be 3. And by and large, you look at 3 nodes, and then you know. You start at the root, and then you read one character from the pattern that decides which child you go to, or if you're already falling out of the tree. Did I say that the query string occurs? I didn't say that. So I might have to make this into an O, right? Or we could say worst case. The worst case is it has to go all the way to the length of the pattern. You don't fall out of the tree early. So you consume one character at a time and visit one more node. That's why it's roughly the length of the pattern that you need. You might get lucky and fall out of the tree early. That can happen. In the worst case, you have to follow down. And then you can either stop in the middle of the tree, but if you append the $, you will always either find a leaf or you fall out. Okay? So that's the cool thing about tries. Let me emphasize that, like, outside of the concrete question. Search in tries is linear in the length of the pattern you're looking up. It's independent of the size of the try. Even if the try is the entire web, you can search for a tree with just four steps down this huge try. It's completely irrelevant how big the try is. I think that needs a bit emphasis because it's really amazing, and it's completely impossible to do that with a binary search tree. It's only possible because we have strings here and we're doing a lot of pre-computation, right? Okay, so if we're trying to find a pattern, what determines the search time is the length of the pattern and only the length of the pattern, maybe the size of the alphabet. Well, I'm assuming that's fixed here. That sounds great. Now I have another question for you. Yeah, we're making a lot of progress today, I know. Just clicking on buttons. It's the same setup, but this time we're focusing on the space usage. Again, you have the answer on the slides, on the phones. Maybe it's more useful to show the slide instead. Maybe we can get a few more votes in. This one seems more clear to you, so maybe I can start showing. At the danger of influencing the rest of you, we have a peak for this answer, and that's the correct one. So theta of n times m for the worst case. What's more important for me is to point out A, how comes, and B, what does it mean? So if I'm going back to the picture, the worst case would be that essentially all strings look like this, one long chain of unary nodes, single child nodes, all the way down to a leaf. You can get essentially that if you have a lot of differences in the early few characters of the strings and then long chains of whatever strings that just have to go all the way down. So by and large, you have for each string roughly its length in unary nodes. And that brings the total space to n times m. The absolute worst case probably is if every string has a unique first character that only occurs in this string, and then the rest can be arbitrary. It would just be appended. It would look like one big jellyfish, or I don't know, a star, dandelion. Okay, enough weird botanical metaphors. So is this good or is this bad? It's a bit depends on the point of view. That's the total number of characters together in all strings. And we need to store the strings somehow. So in a way, it's probably not easy to avoid spending n times m space times the size of the alphabet in a way, or log of the size of the alphabet. We'll come to the compression and coding bits next time, next unit. The number of nodes is n times m. Now, if you assume that we store the strings separately and then build this trie on top just for searching, then it's suddenly not so great. Then we have this additional. So we just double the space, or likely is that the constant factor hidden in this is actually a good deal bigger, because these pointers, these nodes have to be represented with pointers, and they need to store the edge labels. There's a lot of overhead going into this. So probably this constant factor is much bigger than 1. So we're storing our strings, and then we're storing a lot more on top just to facilitate these searches. That's not going to work if the size of the thing you have is really big. If you're trying to index the web, you can't afford to store something that's a multiple times that size. And luckily, it's not necessary for this. So that's the next jump in the evolution of these data structures, from standard tries to compact tries. And the trick is really not that complicated. If you look at the situation from before, this worst case was all these long chains of unary nodes hanging down. And if there's a few in this example, let's just get rid of only those. And in a way, we do that by just contracting them. So it's these two, that's squished into one edge. That's this edge. And this long thing here is squished into just this edge. So the trees, you can basically lay them on top of each other. You would still find how each node corresponds to one node in the standard trie. But of course, now we're losing some information. We just replaced the long edge that contains a whole string by a single character edge here. So how do we know that this second B is there? Or how do we even know how long this chain of things we now pushed together into a single edge, how long that was? To recover that information, the internal nodes in the compact trie store a number. And that's the index in the string that the children compare. So the root always has 0, which says the first, well, index 0 character is what determines the child of the root. But from then on, it could either go one further up, like in this case, or you could jump to 2, where we say all the strings in our dictionary actually agreed on, if they have a B in the first place, they all agreed on the second place, on index 1. Okay? So if you have this compact trie, first of all, if you start with the standard trie, I think it's relatively clear how to get to this compact one. You identify all the chains of unary nodes, and you replace them with a single edge. And the numbers in these nodes is just the original depth. This node was at depth 2, 1, 2, so it gets a number 2. Maybe this is another example. That's 1, 2, 3, and so it gets a 3. How do you search in the compact trie if you don't have this anymore, if that's gone? How do you do the same search as before? Suppose we search for BAB. So we would start at the root. That tells us compare the 0 index character. So that's a B. We follow the edge that matches. Now we're comparing the second character, the character at position 2, index 2, another B. Brilliant. So we go down here, and we have found our pattern. Except that that's not the string that's stored, because we didn't compare this index 1 character. So in a way, we can do the search as before, but when we reach the leaf, we still have to check the missing characters, because we have skipped some. We may have skipped some. So we still have to check if these do also match. Otherwise, it's a spurious hit. But that's the only caveat. Otherwise, the search works the same as before. It even got cheaper, or it at least didn't get more expensive. We don't visit more nodes. We just got rid of some nodes. So the same statement as before holds. You can search in a compact trie independent of the size of the thing. The only thing that matters is the length of the search pattern. And now, as a computer scientist, this is something that pops up so often, but I want to spell this out in detail. If you have a tree and all the nodes are at least binary, have at least 2 children, then the number of nodes is never more than the number of leaves in that tree. It's a simple counting argument. If every node has slots for children and consumes 1 slot because it has a parent pointer, you can set up an equation. How many internal nodes do you have? How many leaves do you have? By matching up the number of slots, taking into account that there's the root that doesn't consume 1. So in a binary tree, it's always exactly 1 more leaf than internal nodes. And in the general case, if you can have even more than 2 children, it's just an inequality. The number of internal nodes is at most the number of leaves, -1. And the number of leaves was the number of strings. That's the number of strings our trie stores. So now we have a really useful bound. The number of internal nodes, these additional things we have to store to search quickly, that's now linear in the number of strings, not in the total length of all strings. So that's a bit more manageable. So I should probably have put this properly. So it's theta of n space, independent of m, which was the length of the strings. All right. So tries are good because they can search fast, but they may use a lot of space. Compact tries make the structure a little more intricate with these contracted edges. Other than that, the rest works the same, and they get the space down to at least linear in the number of strings. So that's the 2 key bits. And so let's wrap up with how well this works. We can use such a trie as an inverted index. It's relatively simple to code that up. If you want to be really, really efficient, maybe you have to spend some thought, but it's relatively straightforward still, and it's quite fast to look up. For our original problem, there may be some things left open. If we just have a list of words and we're storing a fancy dictionary, this is okay. If we're trying to search for just a part, segment of a string, just a substring, or we want to find the occurrences of several strings after each other, then the tries don't really help us much. And even worse, if we have biological sequences or other more general binary data without a specific separation into words, then the try doesn't help us because we don't know what to put into it. It's not so clear.